Um, Welcome back, and this is hopefully the final video to finish probability. Now, I'm not going to touch too much on all of these sampling distributions and the fact that I can have a non-normal distribution which becomes normal. Let's just get started, and let's get started into some exam questions. Even if we sample from a population whose values are not normally distributed, as you can see, the one on the right, then the distribution of the sample will be not necessarily normal, will be approximately normal. And as you increase the sample size n, we're going to get more and more like a normal distribution with less variance and standard deviation. Now, you can see here we've got an example. So the summary is, as we have said, the central limit theorem, that the standard deviation of our sample size, of our sample, is going to vary with n. Now, we've got, I'd like you to please try this now. Okay, you've probably done a few of these before. Okay, I'm going to pause the video very quickly. Pause the video and get you to try it. Okay, ready, set, go. Okay, so hopefully you had a little bit of a go at it, but what we want the probability of battery life. I'm just going to call that B, and we want the probability of B. Now, remember, it's a sample. Okay, it's a sample. So in this case, of course, there's no point using X. It would be making more sense to use B. So a sample is less than 285. That's what we want to find, the probability. Now, in order to do that, well, we need the expected value of our battery life, which of course is our sample mean. And it says here that it has a mean of 300 minutes, and over here we've got 45 minutes. So let's stick to minutes. So that's equal to 300. Now, it says here the standard deviation. Now, the standard deviation is equal to the standard deviation of, B is equal to the sample of 50 computers, 45 minutes. Now, look at this, 50 computers. So the standard deviation of our sample size, our sample, is going to be different. It's 45 over root n, this over here, and that's going to be over root 45. Actually, no, sorry, so my apologies, that's the standard deviation. So the standard deviation is 45, it's over root n, and root n is root 50. Okay, now, of course, we don't, it says here correct to 4 decimal places. We've got to use our calculator. So good old, what are we using? You should know by now. You should know by now. Let's go to my TI Inspire. And what we need to do is we need to go menu 552. Remember, 552, menu 553, and we're going to talk about confidence intervals in a moment. Okay, so let's go menu 552. Now, it says here that we've got here that less than 285. So our upper bound is 285. Our lower bound, our mean, of course, is, what was the mean again? The mean was 300, wasn't it? The mean, I think, yeah, that's right. I'm just trying to, 300. So it's a bit early in the in the morning for me at the moment. And a standard deviation now, it says 45 minutes. Now that's not correct. Here's the problem though, is if you go to 45 divided by root 50, just make sure that it makes complete. Sometimes there can be errors here. Okay, 0.009 is our answer. Okay, so therefore the probability is approximately equal to 0.009. 009 and what is it? 009, etc., etc. I think 2. I didn't have my calculator to the right setting. Okay, so now let's have a look at a non-normally distributed sort of equation. I guess we've got a function here. So between the values of 270 and 290, we've got sort of some function of x. You've got to recall that that the expected value of x is equal to, what was it? Sort of like, sort of from A to B, or in this case, it would be 270 to 290. Like so, of x times f of x. Okay, so x times f of x. So that's x over 200. And we've got here x minus 270 dx. Okay, now I can go ahead and do that. Now, you'll need to do that on a calculator. There's no way you can do that without a calculator. So we'll have to let's go ahead and do that on a calculator. Now that's the expected value of x. Now we're probably we will need to find, so we've got a sample of 30 cups, which means that, well, a sample of 30 cups means that we'll have to find the standard deviation. In order to find the standard deviation, we'll need to find the variance. Okay, and in order to then, using our sample, we'll then have to then, I guess, divide by root n, which is 30. So let's go to our CAS calculator. And now just remember, there's some really good tips here. Shift, I think, minus. No, must be shift plus then. Wow, isn't that awesome? So let's go from 270 to 290. 290 of, and we're going to be very careful here. We're going to have x over 200. So let's use our fraction tool so we can be more efficient. Okay, x over 200, and then that's times by x minus 270 dx, and that's 850 over 3. So our expected value of x is actually 850 over 3. All right, so we found the expected value of x. Now, what's the expected? How do we find the variance when we get a sort of a density function like this? Well, the expected value of what we need to find now is the expected value of x squared. Okay, and that's equal to, well, of course, we've basically got to do the same thing, 270, but this time 290, and this time we've got to multiply it by, this x becomes x squared over 200, so on and so forth. Okay, I'm not going to write it all out because I don't want this video to go forever. So what we're going to do is we're going to go over here. We're going to press enter, and we're going to make this squared. Isn't that nice and easy? And let's see what we get there. Okay. That's quite a big value. Okay. But yeah, that's right. But so the whole point is that we get that answer, and from your methods knowledge, what that gives us is that gives us 80,300. Now, if you multiply that by e to the x all squared, that's minus 850 over 3 all squared, like so. Now that gives us 200 over 9. Now, what have we just found? The question is, what have we just found? We have just found, well, we found the variance. Have we found the variance? Well, I reckon we might have, because let's do the square root of of 200 over 9 is equal to, well, that's over 3. 100, the square root of 100 is 10 root 2. That's the standard deviation. That's the standard deviation of our probability density function I guess we'll call this, we're looking at the volume of coffee. So let's call that the standard deviation of V. See, this is getting a much more difficult, isn't it? There's quite a few processes here. We've got to use this the calculator. We've got to find the variance. We've got to take the standard, the square root. But the problem is that we've now got the standard deviation of V is 10 root 2 over 3. But the problem is that now that we're taking a sample of 30 cups. Now we know what the expected value is. Okay, we can actually sort of work that out, or we've worked that out. In actual fact, the expected value. So the expected value of B is equal to, I think it was, we worked it out somewhere. I think it's 850 over 3. Okay, so we've got the expected value is 850 over 3. Now the standard deviation of V is equal to the standard deviation, 10 root 2 over 3 divided by root n, and that's going to be root 30. Okay, so that's going to be times, so it's 10 root 2 over 3 root 30. Yes, okay. Now, we can go ahead now. It says find the probability. This is our standard deviation. Technically, we could sort of say that that's, if we wanted to, but we don't need to. That's 10 over root 2. 2 over 30 is 15. So 3 root 15. Okay, so you've got to be very careful putting this in the calculator. That's the standard deviation of our sample of 30 cups. So it says here, find the probability of the mean volume of sample. So what we're going to do is, you guessed it, menu 552, and what we need to do is we need to put in our lower bound, larger than 280. So this time 280, how do you get the infinity symbol? Click on the pi button. There it is. What's our mean? We can take 50 over 3. I want to see if this works. Sometimes it doesn't work, this freeze fraction. So I want to see if this works. And the standard deviation is what did we look at? 10 over 3 root 15. So 10 divided by 3 root 15. Be very careful with these things, because does that work? No, it doesn't. What have we done wrong here? What have we done wrong? Okay, I think it's due to my calculator settings. Okay, so menu, settings, you'll be very careful here. Float 3. Why the hell's it in float 3? Okay, let's put it in float 8, float 6, or something. Okay, because it's saying, let's try that again. That's better. 0.9999. And it says to 4 decimal places. So we're looking at the 5th one and it's lower, so there you go. Can you see there? Be very careful with your calculator settings. I did that for a reason. So therefore, the probability that, what are we doing? Looking at V is greater than 280. And what I want you to do now is I want you to say this. I want you to say, given that, and start getting used to this, given that mu is equal to 850 over 3, maybe not for this one, but for the ones later, is approximately equal to 0.9999, correct to 4 decimal places. I hope you learned from my mistake that I made on the calculator. All right, so now we're looking at confidence intervals, and we're really getting into the tail end of the course. So confidence intervals, what do they mean? Well, a determination of a confidence interval for means and that the use of a simulation to illustrate variations in confidence intervals between samples to show that most but not all confidence intervals contain mu. So let's just say we take 100 samples. If we take 100 samples and the population mean lies within that interval, then that means that is a success. And of course, if we have a lower confidence interval, say as 80% or something like that, then it's more likely that our sample mean, or sorry, that our population mean is going to lie within a certain interval. So we're going to talk about confidence intervals. The most popular is 95%, so you really must know this. In actual fact, it must be known as soon as possible that the value, okay, for this, the Z value, okay, now I'm talking about a standardized normal distribution, is actually 1.96. And of course, this would be Z is equal to negative 1.96. This is extremely important because I can almost guarantee you in exam 1, the great thing about 1.96 is it can be used as an exact value, which means that you can do it without a calculator. Because of course, think about 0.96. Okay, 0.04, it's 1/25th, isn't it? So in actual fact, 0.96 is 24 out of 25. So what about if I had 1.96? Well, if I add 25, that's going to be 49 over 25. And I'm going to go through some examples of past exam questions where you need to use that fact. You need to use the fact that 1.96 is the standardized Z score for your confidence interval for 95%, which is the most popular. Look, if I was to be a betting person, which I'm not, okay, I'm going to say that that I'm 95% confident that in your exam you will have in exam 1 you will have a 95% confidence interval question. That being said, in exam 2, maybe a multiple choice, they might ask you a 99% confidence interval because everything can be done in the calculator. Now, that's why I was saying confidence intervals for any quantile. So a lot of the time we could see 90%. You often see, we saw 95, 99. It could even be 99.9. Okay. we can all do this on the CAS, okay, which I'm going to go through with you in a moment. And of course, then varying the sample size. If I vary the sample size, how confident are we going to be that our samples contain the population mean? And I think you'll gather that the more samples we take, the more likely we are. Okay, so we're at 20 minutes now. I do want to be getting through some exam questions very quickly. Now, I want you to just have a bit of a read of this question, and I'm going to pause it right now, okay? And I want you to have a little bit of a think about these sort of things. Of course, you'll have these notes, so you don't have to madly write things down. Now, a confidence interval is an interval estimate of the population mean. Each confidence interval I am getting better, I promise. Each confidence interval is constructed from one sample mean. The sample mean is always the center of the confidence interval. So you've got to think about it's always normally distributed. Centralized around the mean, central limit theorem, we've discussed these sort of things, and the population mean is actually the sample mean as well. Okay, the only thing that changes is this sample standard deviation due to the size. So, what is the average income of the working Australian? I want you to construct a rough confidence interval for each of these sample means. Okay, and I want you to just have a little bit of a think about it. Okay, and I'm just going to pause it now, and we'll come back. All right, we're back, and look, hope you had a little bit of a think about this. Well, how would we test this? First of all, if I was to take a sample of the population or from the population, I don't think you're going to get things which vary so much. Okay, I don't think that this is actually would be considered if I had a sample mean of 70,000, 60,000, and 110,000, then it's probably fair to say that maybe it wasn't a fair survey. For example, if I went to a low socioeconomic area, for example, I grew up in Sunbury, maybe the sample mean would be $60,000. But that's not, have we taken a sample of the population? We've taken a sample of one particular area. Once again, 70,000, okay? I'm just trying to think. It's around about $83,000 is the average income, and that includes billionaires. So of course, we're talking about the average of every Australian. There's around about 26 million Australians. I think it's about 25 million something Australians. Of course, we can't take this sample of 25 million Australians. So what we tend to do is we'll take a small sample. Let's say take a random sample of 50. Over here, this might be if I was to go to the Ivanhoe Shopping Centre and I was to ask each person what their salary is, their average income, then maybe it's 110,000. So you can see here, how do we construct a confidence interval? Well, for starters, the sample mean has to be at the center of the confidence interval. So let's just say a big wide one, let's call it 60,000. Okay, to 80,000. You can see there that 70,000 lies in the middle. Let's do one where we're a little bit more confident on, being in the population mean. Let's just say if the population mean for the average salary was 61,000, and we're pretty close here. And let's just say that we can go 60. It needs to be at the center. So we could say that in this case, for our sample mean, we could go 59,000 to 61,000. That's our confidence interval. That could be a 90% confidence interval, it could be 95, we'll discuss it later. And over here, let's just say that we've got a wider one. But once again, the whole point is I'm going to do 100,000 to 120,000. Okay, you're not going to get this sort of variation if you do a random sample. Okay. Now, confidence intervals, what does it look like? What exactly is it? Well, let's have a look. Here's the population mean. Okay, and as you can see that line, how many of these fall in the population mean? So we've got our confidence interval here. We know that this one does. We know that this one does. This one does not. This one does. This one does. And this one falls right on the outside. So we're going to say yes, it does. So 1, 2, 3, 4, 5. So 5 out of 6 fall within our fall in the population mean mu. Okay. Now, of course, if we were to become 90% confident, then you're going to have more fall in that. So let's go to the 95% confidence interval, which of course is the most important. This is why I said this is the most commonly used in math methods and specialist maths. Now, the theory, what does constructing a 95% confidence interval mean? Well, each interval either has the population mean or it doesn't, just like I sort of said up here. It either does or it doesn't, okay? So, if, for example, if you construct 400 95 confidence intervals from 400 means, you would expect 380 95%. 400 times 95%, which is times 95 over 100. Okay, now of course that's going to become 4. 4 times 95 is 380. So you would expect 380 of them to contain the population mean. Okay, so an approximate 95% confidence interval for mean is found by this. So this, I believe, might be on your formula sheet. You'll have to check. I don't really look at formula sheets because at the end of the day, knowledge needs to be at the fingertips, as I say, as Confucius say. Note that to create a confidence interval, we need a something. I want you to have a little bit of a think about this, and I'm going to answer it in a very, very short while. So I want you to think about, in order to create a confidence interval, what do we need? I'm going to pause it. Okay, so just looking at the formula, you need a mean. We'll call it mu. You also need a, let's say S or sigma. You need a standard deviation. Sigma. And you also need a sample size. Okay, because of course this sample size is at n. So it says here, construct an approximate 95% confidence interval for the average volume dispensed by coffee. We're back to the coffee again. If a sample of 50 cups, so let's write out what we want. We've got n is equal to 50 and has a sample mean of 190. So mu is equal to 190. Take the standard deviation for the population as 5 mils. So standard deviation is equal to 5, but therefore the standard deviation of our sample, V, is equal to our 5 over our root n, which is root 50. That's the big kicker there, isn't it? Now, it says here 2 decimal places, which means that we can use a calculator. And the great thing is that I'm just about to introduce to you a new concept or a new part of the calculator, and that is we're going to go to our calculator. We're going to go menu, then we're going to go probability. Maybe statistics, stat calculations. No, that's not it. Stat results, stat test. Confidence intervals. Now, just so you know, you don't need T intervals, okay? Just your Zs. Now, it says here data input. Now, data, you're never going to need data in an exam because that the only time that is when you're putting in a table of results. We've got to go to stats. Go okay. Now, of course, our sample mean is our population mean. And our population mean is, what is it? What did we say it was? 190 mils. The good thing about this though is that because you're putting in the sample, you don't have to manually work out what the standard deviation is based on your sample size. So it says here we've got 50 cups of coffee, and it says the standard deviation is of the population is 5. So when you take that sample, that's going to take it into effect. Now, does it want the 95% confidence interval? It does. So you press enter. Look at that. Isn't that fantastic? Now I'm going to pause that and I want you to have a bit of a look at it for a second. What do you think would be the confidence interval? So yes, the confidence interval is here, the lower and the upper. That's what you want to see. Forget about the rest of it. This is just what you've put in, and don't worry about ME. Okay, the sample mean, and here is our answer. So I have got already prepared this one for you. The 95% confidence interval is this, and this could be a really popular multiple choice question done in about 20 to 30 seconds if you know what you're doing. Okay, so we can go two ways. What about if we're looking at any confidence interval? So, for example, the theory is that if I'm looking at just a standard normal, okay, now a standard normal has a mean of 0 and a standard deviation of 1. Now, of course, what if I was to do inverse normal, which is menu 553, now I'm going to get you to try this one in a moment, this one here. But what I'm going to show you is where does this 1.96 come from? So this 1.96 comes from, it comes from this. Okay, menu 553. Now we're looking at the area. So if you think about it, if we've got 95% of the data inside it, it means that I'm looking for my Z value, Z value. Now I'm going to put 97.5, or no, it's 0.975. My mean is 0, 1. Look at that, 1.959996. Now what they say is they estimate. So technically that's actually the answer. Okay, that's where it actually comes from. Okay, so it's really important that I guess what we're told in specialists, just like the acceleration of gravity is 9.8 meters per second squared, we're told it's actually 9.81, but we use 9.8. So we're using 1.96, okay, or 49 over 25 as a fraction. Okay, so that's where it comes from. So, for example, if I was to do this, what would be the 90% confidence interval? Well, that would be 0.95, and that would give me 1.64. What about a 90% confidence so I've just done a 90% confidence interval. What about an 80% confidence interval? So that would be 0.9. Okay, which means that I'd have 10% on one side and 10% on the other side. That would be 80%. And as you can see, that would be 1.28, and so on and so forth. All right, but really important to know the 95%. Okay, so this is the general formula, okay, where Z is the approximate quantile. So what we can say is for our standard mean, we can sort of say this value changes based on our confidence interval. Okay, so we noticed there was around about 1.64 for a 90% confidence interval. Okay, so I hope that you understand where that's coming from. Now, I'd like you to try this really quickly. Find Z for a 90% confidence interval where mu is equal to 50. So once again, I want you to find it on your calculator. I want you to be able to work out that when it says data or stats, which one are you doing? Stop here, pause the video and give this one a go. Okay, so the trick to that is that let's just use a standardized normal. Mean 0, standard deviation of 1, and of course we're looking for finding the area. So we're looking for the Z value such that the probability of it being less than that Z value is 0.95. So, and of course the symmetry is 1.64. Now that's another really handy one to know. Okay, so 1.64 was the answer. Okay, that's the Z value for the 90% confidence interval. Okay, now try this. We've got a medical study conducted a phase 2 test on a new drug test with 30 patients. In the sample, the drug was found to increase the life expectancy by 5 years using a standard deviation of 18 months. Construct an approximate 99% confidence interval. Can you do this in your head? Well, you could do it with some things, but you'll need a calculator. So I'm going to get you to give this a go on the calculator, and I'm going to show you the answer. 3, 2, 1. I'm going to pause right now. All right, so I hope you had a go, and I hope you found confidence intervals and Z interval. You changed the confidence interval to 0.99, and look at that. Our confidence interval, our 99% confidence interval for a sample size of 30 patients in a study done with the mean sample mean, the population mean of 5 years. Be careful though, use a standard deviation of 1.5. 18 months is 1.5 years. So they're the sort of little tricky things you got to be careful with. And as you can see, we literally are just putting this, that's our answer. I'm not even going to write it down because you can write that down for me with your notes. Okay, so really essential, common in multiple choice, Z interval, confidence intervals. Change it to stats, as you can see here. Change it to stats. And as you can see then, you can change your confidence interval from 0.95 to anything you like. Do not put in the adjusted standard deviation because it does the work for you, okay? If you have to do it by hand, yes, you do. The sample mean is also the population mean. So that's no issue there. N, of course, is our sample size, and you put it in there, and that's a very useful tool, particularly in your multiple choice. Now, I just wanted to ask you a question. Comparing confidence intervals, true or false? A smaller confidence interval always corresponds to a lower level of confidence. I want you to have a little bit of a think about this. So I'm going to pause the video right now, and I want you to have a little bit of a think about it. So please pause the video. So for the most part, I would have to say that questions, I think the probability topic in general and the questions that have been on the exams have been fairly straightforward. If you can read the question properly, it's actually easy marks for the most part. But there are some trickier concepts which really require you to understand. If you are asked something like this, true or false, a smaller confidence interval always corresponds to a lower level of confidence. Well, let's look at the whole concept of what a confidence interval is. So I've got Z, that's the standard deviation, or it could be S, or like so. And the confidence interval is looking like this. Now, of course, we've got the population mean at the center. Okay, so there's our confidence interval. Now, so therefore, what we can say is that either side of the mean is Z times that's either side of my population mean. So let's just say if I had my population mean of 10, then this would be 10 minus Z, like so, and this would be 10 plus Z over root N. Okay, so is that really helping? I'm not sure, but let's consider this. What we discuss here, we know that for a 95% confidence interval, we estimate that the Z value, so for a 95% confidence interval, our Z score is 1.96, negative 1.96, and of course our mean is sort of in the center here, and of course that's the Z score of 0. And likewise we had for the 90% confidence interval, we actually had a Z score of 1.64 and negative 1.64, like so. Okay, so the question is the what's happening? So the sample size. If I increase the sample size, what's happening to the if I increase the sample size as this increases, then I've got I'm dividing by a a smaller, a larger number, if you like, and then therefore the confidence though means it's getting smaller. So it means that the confidence interval also gets smaller. All interval gets smaller. So what I'm trying to say is that yes, a smaller confidence interval always corresponds to a lower level of confidence. Well, I guess what we're sort of thinking is that if I've sort of got 182 to 184, 180, 80, and 80, then what we can say is that if that's my confidence interval in there, it might be a 95% confidence interval, then I think the main thing that I want to really get across is this whole concept of being able to use this formula here in an exam question. So as it increases, the confidence interval will get smaller, which would make sense, wouldn't it? Because let's say if I sample 150,000 people and ask them, and I ask them what their salary is, okay, that confidence interval is going to be smaller. So a smaller confidence interval, is that true or false? Well, I'll get you to answer that question. What do you think? Is it true or is it false? I think I might have answered it for you, but I'd like you to be able to have a think about it. Okay, so now we move on to hypothesis testing, and of course this is the most common exam 2 concept, exam 2 being your 9 or 10 marks in a multiple choice, the 9 or 10 marks in your extended response. And each and every year, 2016, 17 and 18, there has been sort of 9 to 10 marks in the extended response. That's a very, considering that you have, let's say, 3 multiple choice questions, 12 out of 80 roughly, okay, comes from probability and statistics. They really want to drum this home. They want people to understand this. They want people to understand it more at uni. I did a little bit of it at uni, and I found it really interesting. And as just so you know, as a bit of a side note, if you want to go out and earn the most money from studying mathematics, then statistics and is the way to go. Probability and statistics. There's so many jobs out there for business analysts and actuaries and all of those sort of things. So it is really the way to go if you're after the money. I personally am not after the money, hence that's why I am a teacher. But I love my job. So a lot of my friends who are out there earn lots and lots and lots of money and sit in an office all day and are not happy. All right, so hypothesis testing for a population mean with a sample drawn from a normal distribution of known variance or of a large sample, including. So we've got basically now we're starting it's a new concept, this p-value. So basically what we're going to do is we sort of form a hypothesis. We sort of might question, okay, are people putting on weight? Are people drinking more sugar or, more sugary drinks? We can form what we call a null hypothesis and an alternative hypothesis. And when I ask you to please use this notation, use the notation. Do not make up your notation, okay? Because it is absolute crazy. Because a lot of the notation, if you make up notation for this, you will lose marks. I can promise you. Okay, it was stated by VCAR in the reports for 16, 17, and 18. And then finally, we're going to talk about errors. Okay, now just quickly, I'm going to just pause this video because I'm going to get you to pause it and have a look here. This is the terminology you need in your exams. I'm going to pause it right now. I want to get you to just have a bit of a read of this. Yes, it's in your notes. You might even want to write it down, but notice this. The null hypothesis is H0. The alternative hypothesis is H1. The significance level, which we'll get to a little bit later, is alpha, which is the first letter of the Greek alphabet. And a p-value is a little tiny p. It's the probability of attaining a result. We're basically going to sort of look at we're going to look at a null hypothesis. We're then going to suggest maybe an alternative hypothesis, maybe something's changed. We're then going to test it to a significance level. We're going to find a p-value, and then we're going to make a conclusion. So I'm going to just stop this video. So not stop, I'm going to pause it right now, and I want you to take a good read of this because you need to familiarize yourself with all of this terminology. Okay? I'm going to pause it right now. All right, so we continue, and let's talk errors. So we'll get into obviously forming these tests and looking at a null hypothesis, an alternative, a significance level, finding a p-value, then based on that p-value making a conclusion. But you've got actually 2 types of errors. Now, this is the thing about a textbook, all right? I don't know, I think it's like 16D or something like that. That is one section of the textbook, and that's type 1 and type 2 errors. Now, that is not a lesson because I'm going to tell you this. First of all, you need to commit to memory because you could be asked this question in an exam 1. Is this a type 1 or a type 2 error? And if you don't have knowledge at your fingertips, You'll have the knowledge at your fingertips if it goes in your bound reference. Okay, so in that way you study your bound reference prior to the exams. A type 1 error, I just want you to remember this, is that the null hypothesis is actually true. Okay, so the null hypothesis is true, but what we're doing is we're rejecting the null hypothesis when it is actually true. So if you just remember that a type 1 null hypothesis is actually true, then that's a type 1. The null hypothesis is false when it's actually, we've rejected the null hypothesis when it's actually false. So in other words, if the null hypothesis is false, but we've failed to reject it, so we've said that the null hypothesis is true when it's actually false, that's a type 2 error. There you go. That's 16D, basically. And a fun little fact here is that the alpha significance level is the probability of performing a type 1 error. So, for example, if we have a p-value of, let's say 0.05, this is a very common one, then that alpha is equal to 0.05. Now, alpha is actually sort of our significance level. How much, how much are we prepared to take the risk of it being an error? Well, an alpha value of 0.01, very less likely to make our type 1 or type 2 error. Okay, but in actual fact, the significance level is the probability of performing a type 1 error, which means that we're rejecting the null hypothesis given that it's true. Okay, so it's actually true is the whole point. Okay, so we're going to talk about that more later when we do the exams. Okay, so first of all, if we want to form a hypothesis, what is a hypothesis? Well, you might sort of form a hypothesis that Donald Trump is an absolute crazy man. Okay, now, of course, this isn't the sort of thing that we could, so what we could then do is we could then say, well, what does the population think? Okay, we could sort of say that maybe not, maybe not a great example. Okay, but in this example here, in November 2017, the Australian Bureau of Statistics found that the average weekly earnings of a full-time adult was $1,600 with a standard deviation of $400, and this is what you should be doing in your exams, highlighting the key points. Researchers believe that since then, the average weekly earnings have increased. So, in other words, there's a sign here. Yes, the population mean, we assume the population mean, the null hypothesis is $1,600, but researchers believe that it's increased, which means that the population mean perhaps it's greater than $1,600. A recent study took a sample of 50 people, n equals 50, found that their average weekly earnings was $1,800. The sample mean, for example. What are the null and alternative hypotheses? Okay, so this is all you need to do. The null hypothesis, please do H0. It's simply just the mean. That's all it is. It's the mean is equal to 1,600, and that's always the case. Okay, and the alternative hypothesis, okay, and you do a little semicolon, and what is it? Do they believe that it's less? Do they believe that it's more? It's increased, hasn't it? Or well, they believe it's increased. So mu is greater than. Don't use this $1,800. It's just got to be. It's increased over 1,600. They believe that it's increased. That is our null and alternative hypothesis. It is the easiest marks to get in the exam, but believe it or not, students, for some reason, don't tend to do a very good job of it. Now, in November 2017, let's have a look. Has things changed? We've got this and we've got this, and the reserves have increased. A recent study of 50 people, so it's exactly the same. Describe a type 1 error that could occur in this situation. So a type 1 error is when so really the null hypothesis is true. Okay? So what we could say is that we can say that the alternative hypothesis is accepted when actually and let's talk about in words, the average weekly earnings has not changed. That's an example of an error that we could describe. Now it says find the p-value for this test. Okay, so now what we've got is we've got to consider we've got a sample of 50 people. So I'm going to, and of course, if you've got a sample of 50 people, we could probably do, well, let's find the p-value. What they're saying is that they found that the weekly earnings was $1,800. So we've got to basically now find the probability of what? I'm going to get you to think about it just for a little second. Have a little bit of a think about what might we be wanting to do here. Okay, so I'm going to pause it now. Okay, so our p-value, I hope you have a little bit of a think about it, is sort of the probability that, if we're looking around about, let's say that, let's just call it x. X is greater than 1,800, given that the population mean is equal to 1,600. And of course, because we've got a sample of 50 people, we've got that the standard deviation of x bar is equal to, what have we got? That's the standard deviation of $400 over root 50. Okay, so now we can go straight to our, yep, you guessed it, menu 552. Menu 552. Okay, so we're looking at 1,800 to infinity, which we put in. Now our mean is 1,600. Don't have to standardize any of this, but our standard deviation, of course, depends on our size. So 50 people, 400 over root 50. So 400 divided by the square root of 50. You shouldn't have any problems doing that in your calculator. Okay. Now here's the kicker. What has happened there? Okay, I'm not sure what happened there, but this is what we're trying to do. We're basically finding a sort of our p-value, if you like. And as you can see, it's 0.0002, very, 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 very small. But in actual fact, it says the question is, find the p-value for this test. Can any conclusions be drawn? So the p-value is approximately equal to 0.0002. Very small p-value. But can any conclusions be drawn? No, they can't be drawn because we haven't been given a significance level. Now, a typical significance level is 0.05, or but at the moment we can't. So now if we go down here, this is the sort of thing we're doing. Let's start making a conclusion. In November 2017, it's exactly the same thing, found their average. What conclusions can be drawn when testing at the 5% significant level? So the p-value we have found as the probability that x is greater than 1800 given mu is equal to 1600, and that is approximately equal to 0.0002. So what conclusions can be made? Well, I just want you to think about it. What is the chances? What is the chances of that actually happening? Okay, what is the chances of our probability being of our sample mean being greater than 1800? Just going to stop it there, and I want you to think about it. Okay, so based on exactly the same, as you can see, our p-value is 0.0002. Now it says what conclusions can be drawn when testing at the 5% significant level. So if our p-value is less than our alpha, our significant level, then what we do is we reject the null hypothesis. And of course, we have to, I guess, consider the alternative. But however, if it's above 0.05, we do not reject the null hypothesis. In other words, there's not enough statistical evidence to say that anything has changed. Okay, so in this case, we reject the null hypothesis because we've got this small p-value which is under our significance level. We reject the null hypothesis. Now, sometimes you need to actually word it in the context of the question, which we'll get to later. Okay, now look, there's some of these things identifying hypothesis. Let's just identify what the hypothesis is here. It's all in the wording. A group of people with an advanced lung disease had an average life expectancy of 4 years and a standard deviation of 12 months. A trial was conducted with a new test that changed people's life expectancy. Has it said changed to the better, to the worse? Okay. In 50 patients were given the drug, the average life expectancy was 4 years and 3 months. So what they're sort of saying is that, well, in actual fact, they are. They're sort of saying that in 50 patients that the average life expectancy was more. So the null hypothesis is always the population mean. Okay, so the mean is equal to 4 years. Okay, so 4 years. And the alternative hypothesis is not 4 years and 3 months. They've suggested that this new, a group of people with the lung disease, a trial was conducted on a new drug, which is to help people. So what they're saying is that people are going to live longer. So it's greater than 4. And guess what? That often is worth 1 mark, 2 marks in an exam. Can you believe it? Okay, identifying errors. So we could go through more with identifying errors. I know that this video has gone for longer, but it's getting to the stage where we're so close. A group of people with an advanced lung disease had an average life expectancy of 4 years and a standard deviation of 12 months. So let's do this. Okay, of 12 months. A trial was conducted with a new drug to test whether it changed the life expectancy in 50 patients who were given the drug. The average life expectancy was 4 years and 3 months. Describe a type 2 error that could occur in this study. Now, it's not asking us to do anything, but remember that I said that a type 1 was that the null hypothesis is true, which means that it was rejected when in actual fact it was true. And a type 2 is that the null hypothesis is false. So it was actually accepted when in actual fact it was false. So what we can say is that So what we can say is describing a type 2 error that can occur is we could say that um, we can sort of conclude, so they conclude that the drug, think about what the null hypothesis was, okay, and think about a type 2 error, the null hypothesis is false when in actual fact it's true, conclude that the drug has no effect. In other words, that's the alternative. So when in actual fact, when the drug uh, does change people's life expectancy. So think about what is it? Our alternative hypothesis is basically that the drug works. Okay, what have we just done? A type 2 error. We've said that that H, the alternative is false, when in actual fact the null hypothesis is false. That's sort of the sort of thing we're talking about there. So finding the p-value and drawing conclusions, like it's really the most important aspect as far as your exams. So let's think about it. You're probably likely in exam one. In exam one, you're going to get something I think that could be is fairly straightforward. Okay, let's just say you get 3 to 4 marks, and let's say you get those 3 to 4 marks. Fantastic. But in exam two, last year's exam two, the extended response was easy. So it's probably very important that you know how to draw these conclusions and even potentially be able to maybe even have quite a worded question. Now, a group of people with an advanced lung disease had an average life expectancy of 4 years and a standard deviation of 12 months. Now, be careful. Months and years, let's be careful. A trial was conducted with a new drug to test whether it changed people's life expectancy. In 50 patients were given the drug. The average life expectancy was 4 years and 3 months. Okay. State with reason whether the trial supports the claim that the drug changes life expectancy. This is perfect. Now this could be actually 6 marks on an exam, because they can ask you let's first of all write out. They'll ask us, what is the null hypothesis? The null hypothesis is that the population mean, is equal to, let's do it in years, 4 years, and the alternative hypothesis is that the mean has increased. Okay, you're going to have a sign. What students tend to do is they do 4 years and 3 months here. No, you can't do that. Okay, so we've now formed ourselves a hypothesis. Now what we have to do is we have to do a p-value test, and it's at a 5% significant level. So, of course, this is the sort of thing that would be done over sort of several questions in a calculator. So what we want to do is we want to find our p-value, and that is equal to the probability of let's just call it x. X is greater than, now it says here, life expectancy of 4 years who were given the drug, 50 patients. So what's the mean? I want you to consider how we go ahead and do this. All right, and also consider how do we put it in the calculator. And secondly, I reckon based on what we've done now, I reckon you could do it. So I'm going to pause it right now. Have a go at it now, please. Now, I hope that you've done it, but I just wanted to, this is a deliberate act of mine, because forget all of this. Here's the kicker. Whether it changed the people's life expectancy, which means that our null hypothesis, we don't know whether it's actually equal to, it's not equal to 4. Whenever you see that word changed, then that is that's the question. So the thing is, though, with changed is that it can be changed both ways. Okay, if I was to draw my normal distribution curve, okay, it can be changed this way. It can be changed this way. And what we are really looking for is we want to, if below 0.05, we want to reject the null hypothesis. Now, the problem is with this change is that there's actually, this is like what we call a two-tailed test. Okay, so first of all, let's do the expected life expectancy of a person. Okay, so that's going to be, now this is the expected. We're looking at our sample. The average life expectancy was in 50 patients. So our sample mean is equal to 4 years and 3 months, which is 4.25 years. Okay, we can't use our population mean in this case. We can say also that the n is equal to 50, and we can say that I guess what we've got to do is we've got to find the probability. We've got to find the probability that that sort of our value, expected life expectancy, is greater than 4.25. Given that mu is equal to 4, that's the right way to do it. But here's the kicker, and this is what I'm also going to say. In 2016, 2017, 2018, there has not been a two-tailed test. So is it going to come up in 2019? My guess is yes. Yes, it is. So if you haven't watched this video and if you haven't studied this, then you are likely to probably struggle with this sort of concept. And I'm telling you now, it's due. It is due. Okay, we're talking about 10 marks in exam 2. Okay, so what we've got to do is we've got to find this sort of value over here, and in actual fact, so we've got sort of our mean. We've got our mean of 4, and we've got this over here is 4.25, and of course it goes both ways, 3.75. Okay, so in actual fact, what we can do is we've sort of got to, that's how it's looking. We've got to consider that there's actually we've got to multiply those values there. So how do we do those values? Yep, it's good old menu 552. So let's go there, menu 552. And you know what? I'm just going to go straight up to here. Let's just copy this down, and I'm going to change that. We've done this to death. So the mean is, okay, so the population mean is equal to 4. The sample mean's different, okay? That's different, all right? That's in this case, okay? But what we've got to do is we've got to go from, we want to go from, be very careful. You need to sort of know how you're doing this if you're not doing menu 552. So we're going from 4.25 to infinity. And our sample and our mean is 4. And our standard deviation is 12 months, which is 1 year. And we've got 50 patients. So it's over root n, which is root 50. Oh, that's quite nice. And there you go, 0.0385. Now, this is what I think is going to happen this year. And, you know, you might thank me later when you've got that. Now we've got a p-value, so we've got a p-value for this of approximately 0.03, whatever it was. Okay, but because it's a two-tail test, if I can put it plainly, is when we're looking at this change. When mu and our null hypothesis, our alternative hypothesis is mu has changed. Mu is not equal to 4 in this case. This is what we call a two-tailed test, which has not come up in the exams yet, and I think it will. All right, now, so what you have to do is you have to get that value and multiply it by 2, which of course, forget about the value, we know, state with reason whether the trial supports. Now, what we can say is that, so since P is greater than 0.05, this is the wording you would use, we do not reject the null hypothesis. Because I think it was something along the lines of 0.38, something like that. If you now, of course, at a significant level for a one-tailed test, that would be okay at a 5% significant level. But because we're multiplying that by 2, that's well and truly above that. So therefore, that is actually, one of the hardest concepts for students to get. Okay, so it's getting to the stage where video's dragging on a bit, but we're getting so close. Let's just have a look at the p-value conclusions. P-values, so there's a one-tail versus a two-tail. Okay, whenever you see this changed, mu is not equal to, you see the word changed, for example, that's what we call a two-tail test. Okay, and of course, if I had mu is greater than, mu is less than, and they're suggesting that it's gone up or down, that's a one-tail test. There's a modulus notation for two-tail, which we'll get through a little bit later. We'll look at some challenging questions a little bit later as well. Now, some of these challenging questions I'm going to go through in class. I really do need to go through and talk you through them, and they're going to take some time. This modulus notation, using inverse normal, all of these sort of things. I'm showing you the questions. You're more than welcome to try them, okay? But they are quite some challenging questions. Once again, we've got another one there. You could pause the video and you can try some of these questions. Okay, now let's start having a look at some exam questions. And when I say exam questions, what I'm thinking is I think that this should be done in another video. So we have now finished all of the we've finished all of the content. Okay, so now we're going to just work through exam questions, and that's going to be part 4, which is not bad because in the past we've taken 3.5 to 4 weeks to teach probability, and so far all of the theory has been covered in about 3 hours and 30 minutes. So look, I hope you enjoyed this video. You will get these access to these notes. My advice though is that don't just watch videos. Pause it. Take your time. Take 3 hours. Stop. Take some notes. Try a question. Don't just sit there and passively watch, because if that's the case, then you probably won't get as much out of it. Add things to your bound reference. So have your bound reference in front of you and say, oh, I really like, I'm going to put that into my bound reference. Okay, because knowledge needs to be at your fingertips. So in the 4th and final video, it'll be me going through every exam question that's ever existed for probability and statistics. I hope you've enjoyed this video. I'm sorry that it's been long, but I do hope that it has been useful. Thank you.